Well, this is it. Here we are. It's the Physics 203 video lecture 30, and this is the last lecture. It's just a short review for the final exam. So when's the final exam? It's on Tuesday, the 15th, 3:30 to 5:30 p.m., and we'll do it the way we did the midterm exam. So I'll send it out maybe 15 minutes early, and then I'll accept it up to say 15 minutes later. No big deal there. So same form, send pictures. What I'm going to do now though is the thorough review in terms of what's going to be on it. Okay. So the first thing here is Lagrangian Mechanics. Well, that's kind of general. But we want to be able to put together a Lagrangian. Okay, so L, Q dot, and T, and in fact there isn't going to be any explicit time dependence in any of these, so we've got that. And just a heads up, if we have x and y equals f of x, then we have to make sure we use our chain rule. Then y dot, we've got the f prime of x dot. That's going to come up in a couple of situations. So yeah, we can construct the Lagrangian. The next thing we have to be able to do is small oscillations. Small oscillations, systems of many degrees of freedom. I'm going to go straight to the small oscillations Lagrangian, and then kind of take that apart again for you. So in general, right, we have this matrix of constants. That's J dot, and then we have almost the same thing where this is in the way. I and J, K, I, J, matrix elements, X, I, X, J. Now that's the result of an expansion. However, if you're given a system that's just masses on springs, then you can go very directly to this form. Okay. So that's what I want you to be able to do. Use some masses on springs, and you're not actually doing your second derivative. So I'll go ahead and put all those features down there though. So the Mij from the original Lagrangian evaluated at equilibrium, right? These are second derivative Qi, Qj, evaluated at the equilibrium point. But if you're constructing something with a bunch of springs stretched and compressed and so forth, then you're actually just inheriting these things, and you're trying to put the system into this form. Okay? At which point you can then read off these matrices. So if we were to write this out, the small oscillations Lagrangian, then we have 1/2 m11 x1 dot squared 1/2 x1 dot x2 dot, etc. And maybe then we could say, we'd have 1/2 M22 x2 dot squared, and so on. N times n of them. And in terms of the potential energy, you've got your 1/2 K11 x1 squared. And if there are cross terms, there are also cross terms here. 1/2 K12 x1 x2 and so forth. So you're always factoring off the 1/2, the dynamical variables here, and then whatever is that coefficient is what goes into your matrix. So once you have those matrices, and we're not, we do 2 by 2 or 3 by 3, we don't go bigger than that. Then, etc. Then you've got the matrix M and K. And to get the characteristic frequencies, your characteristic polynomial is the determinant of this matrix minus omega squared M plus K equals 0. So minus omega squared times this matrix worth plus the K matrix, that is a matrix, its determinant equals 0, and that solves, and you solve for omega sub I squared, I equals 1 to n. So yeah, that's a theory where we really have a recipe for it. And yeah, so I'm going to give you one with masses and springs, and you'll be working your way through this process. Let's see what else we have. Yeah, then from the Lagrangian we go to the Hamiltonian. So here, you just have to, and I have about 3 or 4 places where we're going to do this. Some of them are pretty basic, some are a little more challenging. But the most basic one, so the Hamiltonian, I'll just remind you, 1 degree of freedom, you could have L equals 1/2 A of Q dot squared minus U of Q. So what would the Hamiltonian be? H, start, we'll do it 2 steps. Our energy, sum over dL dQ dot QI dot I equals 1 to n minus the original L. And, this is T minus U, kinetic minus potential, and we can just go to T plus U in some cases, but not all cases. In this case we could, but I'm going to have a problem where you can't do that. You actually have to follow this rule here. Okay? So we'll follow this rule in the above case there, and our dL dQ dot is A of Q dot. And then times Q dot again, that's where we get that Q dot squared, and then when we subtract off minus 1/2 A of Q dot squared minus negative plus U of Q. That's where we, of course, just end up with the T plus U again. So that's where we get 1/2 A of Q dot squared plus U of Q. Like I said, in these basic cases, you can just cut to the chase. I've done this often enough, but for a Lagrangian where you're not seeing this form, you're definitely going to want to do this. Now, this is not yet the Hamiltonian, because what we also have is this P equals dl, P is equal to partial L with respect to Q, call that K dot. In our case, P is equal to dl dq dot. What I just had written down, A of Q times Q dot. And now we're going to make the substitution. H is equal to 1/2 A of Q. Our Q dot is P over A of Q, so we have P over A of Q. We're squaring it, P dot squared of Q dot squared, and then we've got plus U of Q. So H of Q and P, we end up with P squared over 2 A of Q plus U of Q. Very simple case. This, of course, is just the mass, and P squared over 2n. Okay, so you want to be able to do this process on a couple of the Lagrangians we have, so there's not going to be anything fancy involved, except for one of them. So this is the basic process. Now, suppose you have a Lagrangian, I'm going to send this up here. Suppose you have one that really does not break down into kinetic plus potential energy. And you have to take this definition really seriously. So you've got your L of Q dot. I'll just put the vectors there, right, for the multiple number of coordinates. And you want to construct the Hamiltonian, you have to go through this step here. So the first step, we could say, well, P is equal to dl dq dot. Do it vector form, that simply means that's all n of them, 1, 2, 3, n. And the second step, of course, is, I'll write it this time as energy, just as before, dl ui dot minus L. And the third step is to get rid of the third step is to eliminate any Q dots in the expression whatsoever, so that it's just in terms of P. That can be algebraically tricky, but we never went to the examples where it's algebraically tricky. So you just have to take these steps. The example I have is actually pretty interesting. Just require these steps, eliminate the Q dots, and you get that. So that's what's to be said about Hamiltonians. There is one problem that's going to require the whole process of Hamilton-Jacobi theory. So let me say a bit about that. I'll do something really closely related. Hamilton-Jacobi Jacobi. So here, say we're given a mechanical system. Say we have a surface of revolution, like a bowl-shaped surface of revolution, x, y, z. Then we have, because it's a surface of revolution, first of all, we've got x, y, z. But the next step is to see, well, cylindrical coordinates would be good. So cylindrical coordinates, that would be rho, phi, and z. And in terms of rho and phi, you'd have L is equal to, say, 1/2 m rho dot squared plus rho squared phi dot squared. And you can inherit that from your plane polar coordinates. Experience shows me that sometimes people want to rederive this expression in the middle of an exam, which is going to waste your time. You're allowed to go straight to the plane polar coordinates version, which is what this is, except there's also the z squared, right? You get the plane polar and the z, and that gives you the cylindrical. That's why you're using rho instead of r, because of that. Minus u, okay? Now, I gave a surface of revolution here. So here, we have z is some function of rho. Z is some function of rho for a surface of revolution. So z dot, which we need to have and square to put into there, is equal to f prime of rho times rho dot. And you can see we're now down to 2 generalized coordinates instead of 3. Okay? Because we have the z dot has this thing there, and that's in terms of the rho dot as well. So good, there's your Lagrangian, and you have to get the correct Lagrangian with all these substitutions in order to get so call that 3 in order to get your Hamiltonian. So now construct H is going to be H of rho and phi, piece of rho and piece of phi. Okay. So then you have to get your correct Hamiltonian along the lines of what we've just been discussing. And from there, you can then set up the Hamilton-Jacobi equation. And if energy is conserved, of course, then you have H of rho phi ds d rho combo. No need for parentheses right there. Once more. ds d rho ds d phi equals E. And then of course we have our techniques for dealing with this, separation of variables and so forth. And that's the only way we're able to deal with it. We have to be able to separate variables, have enough ignorable coordinates in order to reduce the entire problem to one integral. When all said and done, we're just doing one integral on all the problems that we've looked at so far. So a really good example was the central force problem. So with the Hamilton-Jacobi method, you can just run through the central force problem, and so 5, I'll mention some of those techniques. And we have S is equal to S of rho plus S of phi, and then if there's a cyclic coordinate, if you have a cyclic coordinate, you could have S of rho would be alpha sub rho times rho, and if phi were cyclic, S sub phi would be alpha sub phi times phi, and then you keep working your way through the problem. A problem like this, you're going to reduce it to a quadrature or a couple of different quadratures. Then yeah, you're generally not expected to be able to do the integral because we've already done the ones you can do explicitly. So yeah, the Hamilton-Jacobi theory, it's the culmination, and it takes everything that we've learned. Okay? You're working with your coordinates, constructing your Lagrangian, constructing your Hamiltonian, setting up the Hamilton-Jacobi equation, and then reducing the problem to a quadrature. So reduced to quadratures. Okay, so we have that. Now another problem we'd like to be able to set up and reduce to a quadrature is a problem using the Vulpertoi's formalism. I'll write that down. So Vulpertoi's principle that's this variational principle root 2m e minus u dl equals 0. The last time we saw something like that, we called it Fermat's principle. But what we're doing there is we're actually at the level of having set up the Lagrangian. You don't have to have gone to the Hamiltonian in this case. You have to have all the ingredients for your Lagrangian. So your dl is the square root of this thing right here, and when it's also been reduced to fewer variables. When you have that, then because you have a variational principle, you end up with some f of q prime and lambda. But since you have the variational principle, you just get the Euler-Lagrange equations from this, or the Euler's second form for this, and then also reduce it to a quadrature. Should I say more about that one? And the idea is to be able to get the trajectory. So actually, I'll go ahead and example. Your dl might be root dr squared d squared r squared d phi squared. This would be if you had a plane polar coordinates type of problem. And then you express one of these in terms of the other, for example, or in terms of parameter, and then you end up with the entire thing is a function of some variables and a parameter. And then you have Euler-Lagrange equations plus Euler's second form. to work with. And the idea is then to get a trajectory. So I have a problem where we do one thing first and then we find, we do Vulpertoi's principle, keep going with the same problem. So you'll have, the problem will have set, allowed you to set it up in this form first. Indeed. Okay, the last thing that's really important is a central force problem. And this one I'm just going to want you to be very systematic. So we have this is what defines a central force, but we were able to reduce it to a formalism with a real procedure there. So in this case, we're going to end up with plane polar coordinates and everything. That's what I'm referring to. But you start with that force, and therefore you need to take this in sequence. If you're given the force, then you have to find the central force potential, integral F r prime dr prime. So you have to do an integration. That's what gives you the potential from a constant r. Then the effective potential, L squared over 2mr squared plus u of r. Of course, this assumes that you've already gone to plane polar coordinates, right? Your effective potential, and so yeah, actually u of r and L half m r dot squared u dot squared minus u of r, right? That's part of the formalism. So we knew to go to the plane polar coordinates, so we just go from here, set up the Lagrangian. Now the effective potential comes from having set up the energy. So I'll write that because E equals, let me write it the other way around, because 1/2 m r dot squared, 1/2 m r squared v dot squared plus u of r is equal to the energy. Again, that's the kind of thing we've done repeatedly, so we're allowed to just go there. And in fact, when we make the substitution from the conserved angular momentum, that's why we can write 1/2 m r dot squared plus L squared over 2mr squared plus u of r. Right? So that's why this here was the effective potential. This was the effective potential. So yeah, this type of problem, you just take it step by step by step. You can talk about circular orbits, and we can talk about apsidal angle. So continuing here, for circular orbits, apsidal angle. So if the apsidal angle C is 1/2 omega sub phi t sub r, but there was also a formalism 3 plus u double prime over u prime at the circular orbit. So yeah, you're going to want to review those, because if you know this, you can make short work of a problem. If you only know the definition here, you have to do a little more work. Good, so that's our central force problem, a really systematic one, just taken through from A to Z. And that pretty much covers it. Let me recapitulate. Kind of a list of things that we have here now. we have a problem where it's purely characteristic frequencies. Okay, all plural. Frequencies. We have, in no particular order, but since I just mentioned it there, we have that central force. We have that full Hamilton-Jacobi problem, where we really take it from the top, run all the way through to the quadratures. We have to know about how to set up the Vulpertoi principle and solve for a trajectory. And we have to be able to go from Lagrangian to the Hamiltonian. And that's pretty much all of the themes of the semester. There's variational calculus in here, there's Hamilton-Jacobi theory. Good, so I've given all kinds of tips on this, so make sure you know everything we had up here on the board. Anything else we'll do via email. Good, see you guys later.